right now, the smartest AI models in the world are, well, they're basically running out of textbooks to read.
Yeah, they really are.
I mean, they have essentially consumed the entire internet at this point.
Every medical journal, every digitized archive.
Every single forum debate, it has all been scraped, processed, and memorized. So
Right.
if you're building these systems, how do you teach a machine that already knows every medical textbook by heart?
You can't just keep feeding it the same stuff.
Exactly. And if you just feed it like lower quality data from the bottom of the internet barrel, the model actually gets dumber.
It degrades, yeah.
We are hitting what the tech industry calls the data wall.
Which is a huge problem. It forces a radical rethinking of how we actually train intelligence.
Right.
Because if a model can only learn by consuming pre-written human text, its capabilities are permanently capped by the volume of that text.
It's stuck.
Completely. To push past that ceiling, the model has to stop reading and, well, start experiencing.
And that brings us to today's stack of research. We are doing a deep dive into a massive project from researchers at Zhejiang University, Alibaba, and a whole coalition of other institutions.
It's a really impressive paper.
They've built something called OpenHospital, and our mission today is to explore how these researchers are trying to break through this data wall.
And they're not doing it by just finding more data to read.
No, they're building a fully functioning, simulated hospital, filling it with stubborn AI patients, and just forcing AI doctors to practice on them.
And they chose clinical medicine for this arena because, it's arguably the ultimate test of reasoning.
High stakes, right.
High stakes, it's highly ambiguous, and it requires synthesizing all these conflicting pieces of information in real time.
Okay, let's unpack this. If we are entirely out of static data to feed these models, how exactly does building a fake hospital solve the underlying training problem?
What's fascinating here is the fundamental shift from observation to interaction. Current AI training relies on static data sets. So an AI reads a patient's medical record,
Right.
which already has the symptoms, the doctor's questions, and the final diagnosis all neatly written out.
Like a script.
Exactly. The AI just mimics that pattern. It's surface-level observation. The researchers actually compare this to Immanuel Kant's philosophy.
Oh, wow, taking it back to Philosophy 101.
Right. Kant talked about the phenomenon, which is just the superficial object as we perceive it, versus the noumenon, which is the thing in itself, the actual dynamic reality.
So reading a text record is just the phenomenon.
Yes.
Yeah.
But OpenHospital forces the AI to deal with the noumenon. The AI is no longer reading the script. It has to actively write the script in real time based on a changing environment.
That distinction makes a lot of sense if you think about how human doctors learn.
Oh, absolutely.
It's basically the difference between memorizing a medical textbook and actually walking into an exam room.
Right.
A textbook is completely static. You can memorize that a specific pathogen causes a fever and a rash.
Sure.
But an actual human patient might walk into your clinic, complain loudly about their aching shoulder, totally forget to mention the fever, and then just casually drop that they got back from a camping trip.
Yeah, people are messy.
The textbook doesn't teach you how to extract that hidden context.
And that unpredictability is what forces the AI to learn the actual process of inquiry.
It has to learn how to dig.
Right. It has to learn how to navigate ambiguity, ask the right follow-up questions, and adapt when a hypothesis is just proven wrong. That is a vastly different cognitive skill than just retrieving a memorized fact.
Wait, I'm stuck on something here, though.
What's that?
For an AI doctor to actually learn anything valuable in a simulated hospital, the fake patients have to be incredibly realistic.
Yes, they do.
Like, if you just build a simple bot that says, I have a headache, the AI doctor isn't going to evolve any real diagnostic skill. So how do you stop the AI from essentially cheating in a fake environment?
Well, that was the primary engineering hurdle for the team. A simulation is only as good as the resistance it provides.
Right.
So the researchers had to engineer these highly robust synthetic patients, and they use a model called DeepSeek v3.1 to generate them.
Okay, so they used a really advanced model just to play the patients.
Exactly. And they built them on 4 core pillars. They started with the biology clinical correctness. The patient agents are grounded in a massive curated knowledge base of 583 distinct diseases
Wow.
and 467 comorbidities across 19 different clinical departments.
So they aren't just hallucinating random sicknesses. Like, A simulated respiratory infection has to map perfectly to the biological reality of a respiratory infection.
Right down to the causal alignment between the symptoms and the timeline of the disease.
That's wild.
They actually brought in a totally separate model, GPT 5.2, to act as an independent medical evaluator.
Oh, like a grader.
Yeah. It graded the synthetic patients on whether their simulated biology made logical sense, and it scored them a highly robust 4.4 out of 5 for clinical consistency.
Okay, but a biologically accurate robot is still, a
Sort of.
robot. If every patient speaks in perfect, sterile medical terminology, the AI doctor never learns how to decipher everyday, messy human language.
Which happens a lot in real life.
Right. Real people say, my chest feels heavy. They don't say, I am experiencing angina.
Which is exactly why the researchers engineered the second pillar, what they call persona diversity.
Okay.
They didn't leave the patient agents as blank slates. When a patient is generated, the system injects a hidden background prompt into its programming.
Like a backstory.
Yeah, imagine a hidden sticky note attached to the AI patient's code that says, you are a 65-year-old retired teacher who is highly anxious and uses folksy language.
Oh, I love that.
Or you are a 22-year-old athlete who aggressively minimizes their pain.
So that hidden prompt acts like a subconscious filter. It automatically changes the vocabulary and tone the AI chooses to use, but without altering the underlying biological data.
Yeah, exactly. It natively modulates the dialogue. And that leads to the third pillar, linguistic fluency. To prove this worked, they used a specialized medical model, Baishuan M232B, to score the perplexity of the patient's dialogue.
Perplexity. Okay, for everyone listening, perplexity is basically a metric used in natural language processing to measure how predictable or robotic a piece of text is, right?
That's a great way to summarize it. A perplexity of 1 means the text is totally robotic and rigidly predictable.
Boring, basically.
Right. A much higher number means the text is chaotic and random.
Okay.
The patient agent scored a 5.7501, which sits perfectly in the sweet spot.
So it's not too robotic, but not totally random nonsense either.
Exactly. It aligns with professional clinical texts for accuracy, but contains enough linguistic variance to sound like a natural, unpredictable human conversation.
That makes the environment messy in a really realistic way. But, and this is my big question here.
Yeah.
Even if you have a biologically accurate AI patient with a unique personality, doesn't the AI patient inherently know what disease it was programmed to have? Like, why wouldn't it just walk into the simulated clinic and say, hello, doctor, my left anterior descending artery is 70% occluded?
In a poorly designed simulation,
Right.
that is exactly what would happen.
Right.
The AI would just hand the doctor the answer. To prevent this, the researchers implemented a strict epistemic boundary. This is the fourth pillar. Behavioral realism, driven by information asymmetry.
Meaning the doctor and the patient are playing with two totally different sets of facts.
Yes. The patient agent only has access to its subjective experiences.
Okay.
It knows that its chest feels tight or that it gets dizzy when it stands up. The objective ground truth, the underlying diagnosis, the hidden lab results, the actual biology is locked away in a separate vector database.
Oh, that's clever. And for those listening who might not work with database architecture, think of a vector database as a highly organized filing cabinet where information is stored by meaning and context rather than just alphabetical order.
That's a perfect way to visualize it. The patient agent is explicitly instructed by its system prompt not to dump information. It cannot access or reveal the hidden data in that vector database unless the physician agent asks a precise, targeted question that matches the mathematical meaning of the logged file.
So if the doctor asks a vague question like, how do you feel? The patient just gives a vague answer like, I'm tired.
Right. The objective lab results stay completely locked.
The doctor must ask the right questions to trigger the retrieval of the specific medical details.
It creates a genuine cognitive load for the physician agent. It cannot guess. It has to demonstrate active, logical, diagnostic reasoning to unlock the clues.
Here's where it gets really interesting.
Yeah.
You have this perfectly constructed, highly restrictive arena. You have 38 AI physicians distributed across 19 specialized departments.
Right.
And you unleash them onto these realistic, stubborn AI patients who basically lie by omission.
Pretty much.
What actually happens when you run this experiment? Does forcing the AI to practice actually make it smarter than just having it read more text?
The researchers ran a massive 12,000 record experiment, tracking the evolution of these AI physicians, specifically using the Qwen3 Next ADB model over 22 sequential training batches.
22 batches. Okay.
And the results are staggering. They were looking at how the agents adapted over time using a closed-loop reflection mechanism.
Closed-loop reflection. So essentially, the AI is doing a post-game film study after every single patient encounter.
That is the perfect analogy, actually. After a batch of cases, the model reviews the transcripts of its own interaction.
Like watching the tape.
Exactly. It analyzes where it went wrong, it identifies redundant questions it asked, and then it updates its own system weights and internal prompting strategies for the next round.
Wow.
It is continuously generating its own feedback.
And the numbers back up that learning process, don't they?
They really do.
Over those 22 batches, examination precision jumped from roughly 45% to over 61%.
Which is a huge leap.
Diagnostic accuracy, which is the ability to nail the final underlying disease, went from 48% to over 57%. And treatment plan alignment, evaluating the AI's therapy against gold standard human guidelines, rose steadily to 61.5%.
Let's focus on that first metric, though. Examination precision.
Okay.
It measures whether the AI is ordering the clinically correct tests without ordering unnecessary ones.
Which is essentially a measure of not guessing.
Exactly.
In batch 1, the AI acts exactly like a panicked medical intern on their first day in the ER.
Totally overwhelmed.
Yeah. A patient walks in with a mild cough, and the intern just checks every single box on the lab form. Let's order a full blood panel, a chest MRI, a CT scan, and check for rare tropical parasites.
Just everything.
They are just throwing incredibly expensive medical spaghetti at the wall, hoping one of the test results will magically give them the answer.
And beyond just being expensive, that unfocused data gathering actively harms the diagnostic process.
How so?
Well, if you order 20 irrelevant tests, you are going to get false positives or background noise that muddies the AI's reasoning capabilities.
Oh, that makes sense. It gets distracted by its own data.
Right. But by the time we get to batch 22, the AI has shed that panic.
It chills out.
It is acting like a seasoned attending physician. It listens to the cough, asks 3 highly targeted questions, and says, "We only need this one specific viral swab." It knows exactly what it's looking for.
So it stops guessing.
If we connect this to the bigger picture, that precision leads us to what is arguably the most surprising metric in the entire study: system efficiency.
Okay, lay it on me.
The researchers tracked the total input tokens. This represents the sheer computational cost, the amount of text and data the AI has to process in its working memory to reach a conclusion.
You would logically assume that as the AI handles more complex cases and gets smarter, it would need more processing power.
You would think so.
Like it would have to juggle more tokens.
But that is what makes this a breakthrough. As the AI evolved across the 22 batches, its computational cost actually dropped.
Wait, really?
Yes, it went from processing 16.04 million tokens per batch down to 14.83 million tokens.
It got smarter, but it used less brain power to do it. The post-game film study actually worked.
Through that reflection mechanism, the AI isn't just learning facts about medicine, it is learning efficiency.
Wow.
It realizes that starting an exam by asking about family history of liver disease when a patient has a sprained ankle is a total waste of computational resources.
Right.
It stops exploring dead ends. It streamlines its entire logical pathway, taking the most direct route from symptom to diagnosis.
It is actively optimizing its own reasoning logic. That's incredible.
It really is.
To prove that these abstract efficiency numbers actually mean something tangible, let's look at the specific case studies from the source material.
Yes, let's do that.
Because it's one thing to say the accuracy went up, it's another to see what that looks like in the clinic. Let's take the case of patient 0419.
Patient 0419 is a perfect showcase of how a single agent evolves its reasoning over time.
So patient 0419 comes in complaining of a severe sore throat and fever. In batch 1, the AI doctor is that panicked intern we talked about. It orders a nucleic acid amplification test, an AST liver enzyme test, and a specific culture for Neisseria gonorrhoeae.
It is totally unfocused.
Right. And because an AST test measures liver damage, which has nothing to do with a standard sore throat, the AI gets confused by the scattered data.
The noise we mentioned earlier.
Exactly. It confidently and incorrectly diagnoses the patient with gonococcal pharyngitis.
And because the diagnosis is wrong, the treatment plan it generates scores a dismal 0.36 for alignment.
Ouch.
It prescribes heavy antibiotics for a disease the patient doesn't even have.
But fast forward to batch 22, the exact same AI agent is presented with the exact same initial symptoms for patient 0419.
Same exact starting point.
This time, there is no liver test, no random bacterial cultures. The AI orders precise, targeted tests, a syphilis serology, a standard throat culture, and an Epstein-Barr virus antibody panel.
Very specific.
Based on those specific focused results, it correctly diagnoses a viral infection, and its treatment plan scores a highly aligned point 0.8.
It's a complete night and day transformation in competence.
The individual growth is just remarkable.
It is. But the second case study they documented is even more profound, I think, because it moves beyond individual reasoning and illustrates what the researchers call collaborative necessity.
Oh, this is where those 19 different specialized departments come into play, right?
Exactly. We have a 52-year-old simulated patient named Amanda Peterson. She presents to the clinic with a fever and dyspnea, which is difficulty breathing.
Okay.
The AI physician assigned to the Department of Infectious Diseases takes her case.
Makes sense. She has a fever.
Initially, this agent does a solid job. It evaluates the symptoms, navigates the vector database, and correctly suspects infectious endocarditis, which is a dangerous infection of the heart valves.
But the heart isn't the infectious disease doctor's specialty.
Right. And this raises an important question. What happens when a language model reaches the limits of its own programmed domain knowledge?
Usually they just make stuff up.
Exactly. In a rigid, older system, the AI might just guess, or it might confidently hallucinate a complex cardiology treatment plan, which could be disastrous.
Truly.
But in OpenHospital, the infectious disease agent has been trained to monitor its own confidence levels.
Oh, wow.
When it realizes it is out of bounds, it autonomously triggers an external call to the cardiology AI agent. It requests an urgent cross-departmental consultation.
It literally pages a specialist.
It does. The cardiology agent reviews the entire transcript of the patient encounter.
Okay.
And it doesn't just blindly agree with the first doctor. It brings its specialized training to the table. The cardiology AI recommends starting with a transthoracic echocardiogram, a TTE, and then escalating to a transesophageal echocardiogram, a TE, to get a better look at the heart valves.
Very thorough.
Crucially, the cardiology agent explicitly warns the infectious disease doctor against premature immunosuppression until the infection is definitively ruled out.
That is genuine multi-agent debate and consensus.
It is.
You have two distinct AI entities with different specialized training weights, arguing over the best course of action, checking each other's blind spots, and synthesizing a safe clinical pathway together.
They're creating new knowledge through collaboration.
And I guess that highlights why those 467 comorbidities built into the fake patients are so essential.
Oh, absolutely.
If the synthetic patients only ever had simple textbook diseases like a broken arm or a common cold, the agents would never be forced to talk to each other.
Exactly. The messy, interconnected biological complexity of the arena is what forces the emergence of that collaborative intelligence.
Okay, this all sounds incredibly futuristic.
It does.
But we have to do a reality check here. If you are listening to this on your commute and wondering, should I be asking OpenHospital for a second opinion on my next diagnosis, we need to ground this in the actual limitations outlined in the paper.
Good idea.
We are not quite ready to hand over the keys to the clinic, are we?
We are definitely not. The authors of the paper are very clear about the current constraints of the system. First and foremost, OpenHospital is currently a text-only modality.
Right.
Real medicine is deeply multimodal. A real doctor doesn't just read a text transcript of your symptoms. They look at the color of your skin, they listen to the specific pitch of your breathing, they review the visual nuances of CT scans and ECG waveforms.
So you cannot just text a picture of a weird rash to this system and expect a perfect read.
No, you can't.
The environment lacks visual and auditory context.
Exactly. Specialties like radiology or dermatology are entirely reliant on visual data, which this current text-based abstraction simply cannot process.
Makes sense.
Furthermore, the simulation simplifies the temporal progression of disease.
The element of time.
Right. In the real world, a patient's condition is a continuous timeline. Vital signs fluctuate by the minute. A patient might respond poorly to a medication on Tuesday, crash on Wednesday, and need a totally different intervention by Thursday.
But the current OpenHospital system gives you like a complex snapshot, but it struggles to model that continuous, messy passage of time.
Yes. That fine-grained, dynamic time progression is incredibly difficult to simulate computationally right now.
Sure.
And then, of course, there is the data security aspect.
Yeah.
Medical data is arguably the most sensitive, highly regulated information on the planet.
Which brings up a massive technical advantage of this specific project. OpenHospital uses 100% synthetic data.
Yes, 100%.
There are 0 real-world patient records, no protected health information, Nothing from actual humans in this entire database.
Because it is entirely synthetic, it elegantly bypasses the regulatory bottlenecks that usually slow down medical AI research.
It's totally clean.
It is fully compliant
Hmm.
with major privacy frameworks like IPA in the United States and GDPR in Europe. There was no risk of a data leak because the patients literally do not exist.
Right.
But the researchers stress heavily. This makes it a safe sandbox for researchers. It is strictly a benchmark for evolving and testing AI architectures. It is absolutely not a clinical decision support tool for actual patients today.
So it is a training ground for the AI of tomorrow, not a hospital for the patients of today.
Perfectly said.
So what does this all mean? Let's zoom out and look at the journey we've just taken.
Okay.
We started with a massive problem. AI hitting the data wall, running out of human books and articles to read, and facing a hard ceiling on its intelligence.
Right.
But the solution isn't just vacuuming up more low-quality data from the internet. The future of AI development is about building complex, dynamic, simulated worlds.
Yes, simulated arenas.
By forcing AI doctors to practice on stubborn, highly realistic AI patients who hide their symptoms in vector databases and force the AI to actively reason, the models actually evolve.
They get demonstrably better.
They become sharper in their diagnostics, they become cheaper and more efficient to run computationally because they learn to stop guessing, and they learn the necessity of highly collaborative cross-departmental teamwork.
And if we look ahead,
Hmm.
that brings up a truly profound implication, especially as these researchers plan to integrate vision language models and temporal disease progression in their next iterations.
Oh, man.
Think about what we've seen today. These AI agents have evolved sophisticated collaborative intelligence purely through text-based arguments over simulated symptoms.
It is literally just code arguing with code on a screen.
Exactly. So what happens when we upgrade these arenas with full visual, auditory, and real-time temporal physics?
Yeah.
What happens when the AI can mathematically see the simulated sweat on a patient's brow or hear the slight wheeze in their simulated lungs over a period of simulated weeks?
That's wild to think about.
Will the experiences generated inside these closed synthetic loops eventually become so rich, so nuanced, and so complex that they actually surpass the quality and depth of the original human data we used to build them in the first place?
Are we building a simulation that is eventually going to be a better teacher than reality? That is definitely something to chew on.
It really is.
Thank you for joining us on this deep dive. Keep questioning the world around you, and we'll see you next time.